Thank you, Liqun, for your wonderful introduction. And thank you, Sujin, and the entire organization committee to invite me to speak here. That's my honor to talk about this work. So today I wanted to present our new work, but in order to do so, I would like to give you a, I don't know why it's not moving.
Perhaps, yeah, now it's going.
Okay, but the mouse, I don't know. Okay, so in order to introduce a concrete scheme, we call the Polaris. I think first I will give you some background. For example, first I will introduce you the what's the problem here I want to tackle. So which is privacy problems in the blockchain networks. So usually when you do communication, then you have sender, you have receiver, and you have content. Then here in the blockchain, we call the transaction. So how we protect this? The important tools or people think is more practical tools, which brought in the practice is the zero knowledge proofs. So that's I will do an overview for the zero knowledge proofs and introduce some known schemes, which are called the zkSNARKs. So the zk called zero knowledge, SNARK, Succinct, non-interactive argument knowledge systems. Then I will give you a concrete example, which is the Polaris. So this is the transparent setting, and for the circuit, we call it the Rank-1 Constraint Satisfaction circuit. Then I will show you those evaluation. This is just more like the initial results, so not actual implementation, but it is like the C language implementation and some comparisons. Okay. So, yeah, I think I don't know, my arrow not working, but the mouse seems not doing well. Okay, so first we look at the concept of the blockchain. So basically, blockchain is a decentralized peer-to-peer ledger system, which is again not of interest as a possible solution to many applications. So today I may not talking about those applications. For example, like the decentralized finance with the nickname DeFi and the decentralized identity management, supply chain management, and so on. You can list a very long list. The reason is people or government come to this point because the blockchain can provide the tested, like the trusted consensus and trusted computation, also the immutable data between untrusted identities. So we look at so this is a figure show what blockchain, the property of the blockchain could offer. If you look at the left side, so basically the data is immutable, which means once you upload it to the blockchain, then they can be cannot be changed anymore. So that will be there forever. And also it's time stamped. So any transaction will have time step, which also put into a block. And any transaction also can be a program. For example, like a smart contract. So which is you can upload the program into the blockchain. Of course, the future is they are distributed systems, and each participant in the system will have a full copy of ledger for full transparency. So this is what the virtue of the blockchain when they invented in the 2008 for the Bitcoin blockchain. Then they have anonymous. So this is comes out, you will have multiple public keys. So your public keys is associated with your wallet. However, from the practical side, possibly it is, you can provide a certain anonymous. However, many research papers already found they can link whatever, how many public key you used or those pseudonyms, then they can link to the actual wallet. How about the privacy? Basically not there. As I mentioned, when they created the Bitcoin, the virtue is transparency. So there is no privacy at all. However, since many applications come along the way, and the privacy is a required properties. Okay, last one is anonymous. So basically, is when you can put a block, is each miner has to agree on something. So is everyone has to agree on. So that's why it's like the voting is anonymous voting. Okay. I'm so sorry, I think. Then we look at the those blocks and what's in the detail, how the blockchain is formed. So for each block, then you will have, so those are the basically transactions. So each block not including one transaction. Basically here I put the 64 transactions. So this is the format in the Bitcoin. And you will have those, so this is the body text. Then in the header, then you have the nonce, you have the targeted bit, you have timestamp, then you have Merkle root. So basically, then this 64-bit, 64 transactions will apply to the Merkle tree to generate the Merkle root. So they only store the Merkle root in the header. Okay, then you will have the hash function from the previous block. Then you have the version number. For example, currently the version 48. And then this is the new block, the hash. So basically you hash entire those header and put into here. Then you look at each block. So each block, then how you connect it. Because you connected in this way, this is the previous the hash. Then next block, then you hash this. Okay, so basically blockchain is a linked list of blocks. How you link them? By hash chain. So each of those will be the hash function connected. So in the crypto, we call this is a hash chain. Okay, so this is the block structure. Now we look at in more detail. So in many of those cryptocurrency, then they use the model called the unspent transaction output models. So you look at here, so basically the transaction, then you will have input, then we said this UTXO-B, and the output will be two UTXO. One is C labeled, another labeled the D. And the C has the 0 point Bitcoin. So this is Bitcoin structure I'm writing here. And the owner will be the Bob. And the D will have 1.5 Bitcoin, and the owner is Alice. Okay, so we look at the system state, and the currently state will be like this. UTXO-A, then have value is 1 Bitcoin. Owner is Alice. And the UTXO-B, and the value is 2 Bitcoin, and owner is Bob. So what here? So Bob wanted to send the 0.5 Bitcoin to Alice. Okay, so you look at the output. So that's transaction A not changed. Then transaction C, I'm sorry, so that's they send the 1.5 because Bob has 2, so he sent the 1.5 to Alice. So this is transaction D, and he remain has 0.5, then this is sent to himself. So his original UTXO B becomes the UTXO C, owner is Bob. So he only have 0. Bitcoin, okay. So when you look at the format, how you do this? So basically you digital sign those. So for example, the first block, usually we said is a genius block. So those comes from the Coinbase. So you do not have a previous block, okay. So now the first owner, then he has his own key pair, public key and private key. Also, how much money he has there. Okay. So now he will digital sign the message M. So message M will be this. So input 1, so which is here, and his public key, that's sender's public key, PK2, receiver's public key. And the amount T1 is how much he wants to send to the receiver. Okay, so that's he will digital signed. You see, each of those, not just a hash chain chained together, also digital signature chained together. So this is raised another problem called the scalability of blockchain. But here I won't talk that problem. I only talk about the privacy. Okay, so which means all of those public key and the amount and the receiver and the sender, those are all in transparency mode. Everyone can see. So the problem is how we can achieve the blockchain privacy, or in other ways, how we can share the sender, receiver, and the transaction privacy. For example, in UTXO, then currently tool is zero knowledge proof systems. Okay, so then we turn our interest to look at this. Okay, so here I do not introduce you like the very accurate definitions. I will just introduce you more like the demonstrated the concept. So in general, loosely speaking, then zero knowledge proofs are the proofs which yield nothing beyond the validity of the assertion. For example, prover and the verifier can back and forth communicate many times. However, at the end, verifier only knows the validity of what claim prover wanted to say, nothing beyond that. Okay, so let us look at the example. So Alice, we said is a prover, Bob is a verifier. So Bob said, okay, I have 1 Bitcoin. I'm sorry, Alice said, this is his claim, said I have 1 Bitcoin, or could be the claim like I uploaded the data for product, for example, organic salmon. And this is verifier Bob. Bob wants to accept this. So Bob think, I believe X is true, but I do not know why. Okay, so the zero knowledge proof, the definition will be like completeness. So if the statement is true, then prover can convince the verifier this is true. However, if the statement is false, then prover cannot convince the verifier. So this is we call the soundness. So for the proof system, also you have like the information theoretic. So usually we call the proof, but have another concept called the argument. Here I won't go to very detail. So usually when we talk about argument, which means computational bounded. So in this case, soundness. So the prover cannot convince verifier, or we could say prover can convince the verifier with negligible probability if the statement X is not true. So that is under bounded the computation. And the third one will be the knowledge, zero knowledge. So in this case, the verifier learns nothing except for the validity of the statement. Okay, so this is the general concept, the completeness, soundness, and zero knowledge. Okay, then we look at a concrete example. So this is a textbook setting. Then this is for Diffie-Hellman setting. So prover is Ines. What does he want to prove? He wanted to prove I have X such that Y equal to G to the X. So usually we know in the DH setting, X is a private key, Y equal to G to the X is public key, and the G is a generator. Okay, so now he wanted to prove to the Bob, said, hi guys, this is my public key. I can prove to you I have the private key such that this public key equal to G to my private key, which is X. Okay, so there's two ways to do this. So the upper part is interactive way, the lower part is non-interactive way. Okay, so for the interactive way, what he will do, he first sends the R. So that's the random number, which is computed as the G to the K. Okay, K is randomly chosen. Because K is randomly chosen, so R is a random number. Then Bob will randomly pick up C and send it to the Ines. Okay, the Ines will do, he will compute S, which is K minus C X. So now he will send S to the Bob. Then Bob will verify this entity, whether R equal to G to the S times Y to the C, because those are all he knows without knowing the X. So if this is true, then he said, I believe X is true, but I do not know X. Okay, so this interactive way can be converted to non-interactive. So what Bob Ines will do here, he will just compute the G to the K without Bob choose the C, then he hash this to get the C. Then he computes the S and the same thing as here, and Bob will do the same verification. Then he will conclude, I believe X is true, but he does not know the private key X. Okay, so maybe if you already took some cryptographic course, then you will know this is Schnorr identification scheme, and the below one is the digital signature schemes, right? Yeah. So then the values here are we usually call the commitment value, and the C called the challenge, and the S called the response. So this is, I mentioned then the first one called the identification scheme, which is the inactive, interactive one. And the second one called the Schnorr signature schemes. And also they have another name under the concept of zero knowledge proof. This is also referred to as knowledge of exponent, KOE, or in the Peterson's commitment scheme, they also called the proof of representation. Okay. So for any zero knowledge proof system, how we measure the efficiencies, then we will measure the prover's complexity. So this is the computational cost for the prover to run the protocol. Then we will look at the round complexity, which is the number of the transmissions between the prover and the verifier. And the proof of the length or communication, which is the total size of communication between prover and the verifier. Then we look at the verifier's complexity. So it's computational cost for the verifier. Also, another cost we wanted to look is setup cost. For example, like the common reference string, which use in the zero cache, then that's the cost there. Okay. For other scheme, many other schemes, actually they do not have much this setup cost, except for the zero cache. Okay. So, however, we ask more. It's the problem is integrity of computation, because the protocol you just see, it's proof of KOE does not say anything about integrity of computation. However, another more important problem is, for example, Alice wanted to prove to Bob, which is a verifier, said he hashed the value. He has the hash function H, and he gave the Bob Y, and he said this is the hash value of the X. So how Bob is sure Y is the image of the X without knowing preimage X? Okay, so this is the symmetrical key setting, basically. Okay, so from public key setting, you can base on some hard problem. Okay, however, for the private key setting, symmetrical key setting, like the hash function, how you prove the preimage? Or you could think this is more like the inverse, right? You given the Y and ask you proof Y is the image of H at the X, or you could prove X is the inverse of the Y. How you can do this? Okay, so this is done by what we call the verifiable computation. So verifiable computation, basically they will represent any algorithms or programs as a circuit. So basically you extend your statement or algorithm into very low level language, which is a circuit, the way you implement those statements. Okay, so for the circuit representation, so usually we will assume you have a very large field, then you have the circuit, like you have 3 input here, 1 output. Then we assume those circuits only have 2 types of the gates. One is addition gate, another is multiplication gate. So which means those gates maximum have the 2 input, 1 output. Okay, for example, in this case, we have first gate is addition, second gate multiplication, and the third gate addition, multiplication. So this is the output, then this is the input. If you choose the value A, B, C, then those you will have value. Then those called the wired value when you do the actual implementation. Okay. So the question is how the prover can convince a verifier. Then you will have that CW equal to 1 without reveal any information about the W. What is the W? W usually we call it the witness, which consists of value from the input and those intermediate wire values, not output, because output we will give to verifier. Okay, so it's all those intermediate gates wire values. Then this is we call it the witness. So basically you extended or you stretched your program or algorithm into the circuit. Okay, so most popular one proposed for the blockchain privacy or those auto-source computation in cloud applications. It's this scheme called zkSNARK. So I already mentioned it before, ZK is zero knowledge, S is succinct, and the N is the non-interactive, and the AR is argument, NAS K is knowledge. So what's this? Basically, zero knowledge, as we already mentioned, which does not leak any information about the witness. Succinct, which is talking about the proof size. This proof size is independent for any NP witness sizes. Or we could say is a computation complexity of prover, verifier, and the communication, including the proofness, are computationally bounded. And the non-active, which means only one message is sent by prover. And argument of the knowledge, in fact, the argument or proof, they have distinguishing here, but here I won't go to detail about this. So in general, framework of the zkSNARK. So this is, for example, we given an algorithm. So what we will do, first we will convert this algorithm or the program into a circuit. Of course, this is also very hard work. It's not for research here. Then we will encode, then we get a circuit now. So all those are called the circuit generator. Then once we get a circuit, then we will encode this circuit to a quadratic arithmetic program, or we will encode it as a constraint rank-1 constraint satisfaction. So either QAP or R1CS. Then once we have this, then we will encode this to polynomial. Okay, it's a univariate polynomial or multivariate polynomials. How you can do this? Lagrange interpretation. So this is the kernel part of zkSNARK. Okay, so you deal with the polynomials. Then you build the argument to prove something about the polynomials. Then there's two ways now. Either is based on the homomorphic encryption, which is based on some hard problem, and another is based on the probabilistic check proof, PCP, or this is maybe implemented with the error correcting code, for example, Reed-Solomon code. Okay, then how about the zero knowledge? How about the non-interactive? Then you will add the zero knowledge and using Fiat-Shamir transform to convert interactive to non-interactive. If this is not done in this steps 3 and 4, so now you have your proof ready to send it to the verifier. So this is the diagram. So you have algorithm, for example, SHA-3, or currently in Zcash is SHA-256. Then you will decompose this SHA function into the circuit. Okay, or you could look at the high level is the C program, and from C program you will look at the low level logic, which is the circuit generator from your C program into the circuit representation. Then you encode it as the QAP R1CS or read Solomon code or no degree polynomial. Okay, so those, then you go to the crypto engine. Either it's some hard problem based like the public key or just a symmetric key. Then you send it to the verifier and the verifier make a decision. Okay, so this is the general framework for zkSNARKs. All of them doing all of those things, just using different methods, either uni or multivariate polynomials or homomorphic encryption or PCPs. Okay, so this is some recent zkSNARKs. For example, right now we think you already have your circuit. Okay, then the most early ones, which are already in the practical system, is QAP or QSP based. So that's first published in the 2013 called the GDPR, and then the Zcash first implemented this version, BCTV 14A. So that's the first implemented. But they got attacked, so currently they moved to GORS 16. Okay, so the setup is private. So basically, they need the setup, for example, like those public keys, G to the A1, G to the AB, G to the AC. How many of those lengths of your circuit or number of the multiplication gate? Okay, you can imagine. So when they set up this, then how about the private key? Then they said that they destroyed. So, okay, so then you could imagine, we have to trust them, right? They said that they destroyed. And the security is based on the knowledge of the exponent. Okay, then implementing like the Zcash using the decentralized, and the Pinocchio's also is a version of BCTV 14A, and the Zcash currently using GORS 16. And the Hawk is the application based on the Zcash. Okay. Then, so those are based on the discrete logarithm, bonnet proof, and the Marlin. Marlin also private setting, but their common reference string is updatable. Okay. So this is relatively new in the 2020. And the Spartan, which was published by SETI in 2020. So this is the first zkSNARK provided general format for polynomial commitment, in which you can switch to any polynomial commitment schemes. So this one, he using the discrete logarithm, but those are just experiments. Okay. Then the last three is basically transparent setup, and the security just based on the collision resistant hash function and the pseudo random number generator. And so that's Ligero, which is Ligero cryptocurrency. It's that they already implemented and put into their actual product. And the Stark, they implemented called the Liber Stark, and the Aurora implemented in the Liber IOP. So then we look at their syntactic complexity. Okay, so GORS 16 or GDPR is a setting will be the same. Then they need to have how many elliptical points. So will be the linear in the size of the circuit, which is n. And the proof time always n times log n. And the proof length very simple, 3 elliptical points. And the verifier also computes 3 pairing. So in addition to they are, have a very large common reference string in the setup, they are very good for the blockchain application because those computation is miner will do those computation, right? User will do the prover computation. Then this is the arithmetic circuit. And the Ligero Aurora, the Ligero, that's proof size, the prover's time all the same except for the Spartan. Spartan just linear, okay. And for the Ligero, at the proof size is the square root of the n, but the verifier time is the linear of the circuit size. And similarly as the Aurora, Aurora reduced the proof length from square root of the n to the square of the log n. Okay, and the circuit also generalized from arithmetic circuit to R1CS. Okay, and the fractal and the Spartan random oracle model will have a similar things for the prover time and the proof length. However, verifier time from linear to log. Then come out of the work. Then work is both work and the SNARK apply to uniform circuit. So this is a more specific circuit now, but their prover size and verifier time is in the log scale. And the Merlin, as I mentioned, it's private citing. However, it's updatable for their CRS, and they also has this log case. And the Spartan, if you're using the discrete logarithm, and the proof size and the verifier time will be square root of that, okay, instead of the log. And this is our new work. We call it the Polaris. So syntactically, we have compatible bound for the proof length and the verifier times. However, the concrete, for example, this big O here, this constant could be very large, but we could do very small. Okay, so now we look at the R1CS relation. So basically, right now, I will assume we already get this R1CS relation from the program. So we're using the circuit generator, we get the circuit. From the circuit, we get those matrix A, B, C. So basically, those are the left input vector. B will comes from the right input vector. C is output vector. Then from that wire values, then we know that we can write as the 3 matrix. And V is public input and output vector of the instance. And W is private input vector of the instance. As I mentioned you, for example, this is a previous circuit, just 1 bit output. And we assume that at most n non-zero entries in each matrix. The reason is those matrices are very sparse. Okay, so that's also the information we use in our design. Okay, so now then we have this relation for the R1CS. So this is the vector, including the public input and the witness. So witness, you could think it's just private information because it's input and the wire values. Okay, so then you will have the NEF matrix, NEF input, which formed as the matrix A times this vector, which will be your NEF input vector. And this is your right input vector. This is your output vector. So of course, then this is bitwise product. Then you get this 0 vector because this is output equal to left input multiplied by the right input. So that's why here we only consider multiplication gate. Okay. So what's the goal of zkSNARK? So zkSNARK is trying to prove this without giving W. Okay, you could think about the V here, just 1 bit. Okay, then without giving W, you prove this entity is true. Okay, then why we directly consider R1CS? Because this is more general than the arithmetic circuit. Okay, so as I mentioned, that's ABC basically represent the left input vector. This is right input vector and the output vector. So that's why R1CS is more general case. And for example, if we wanted to prove any transaction, UTXO in the Zcash, currently they're using the SHA-256. So basically we want the prover give you Y, which is the output. And the SHA-256, X will be here. So just the input part of the W, okay. So how you can shade this? So basically, this is the way you shade. You without giving the X, then you prove to the miners. Then this is what in the transaction. Okay. So zero cache basically, the cache basically implemented the goal 16 to achieve this goal. Okay. So for the encoding of R1CS relation, which means we get a matrix now, then you will have the two ways to interpret those metrics. One is interpreted as multivariate polynomials, for example, Spartan, and another is using univariate polynomials, for example, Gore 16 and Aurora, those are the univariate polynomials. However, they will transfer, for example, this is matrix, then this is, for example, just one column, then this is your polynomial. But you will transfer this to prove this statement is true, transfer to your random pickup point and compute this evaluation is true. And this big square will be your big field, originally in the small range, but now you enlarge it to the bigger range. So that's why usually we call this small range give you the polynomial with no degree. Because compare, for example, if we want to achieve 128-bit security, our field will be the 2 to 256. So the degree could up to 2 to 256. But if here is SHA-256, then maximum multiplication gate is about 23,000. So which means the degree here is maximum 23,000. So compare with the 2 to 256, then we said this is no degree polynomial. Okay. Okay, so those, then what's our Polaris? So for the Polaris, basically we have two protocols. One we call the product check protocol, another called the univariate sum check protocols. So for the first protocols, first we were encoding matrix to bivariate polynomials. For example, yeah, each row is one univariate, but all rows then will be the bivariate polynomials. Then we will execute a polynomial commitment protocol. So which means we will employ a polynomial commitment protocols. Then we generate the proof that in this case, verifier will verify this. If it is true, then continue second protocol. Second protocol will involve 3 sub-protocols. First is the prover and the verifier will together run no degree test. So this is the initial phase in the no degree test. After that, they will run worker tree commitment schemes to commit 2 Reed-Solomon cohorts. And the third, then they will together to run the GKR protocols. Then in the final phase, they generate the proof. Then they will do the verification. Okay, so in the coming few slides, basically is a lot of the mathematics. So possibly I will just quickly skip that. So basically it's how you conversion. For example, how you convert it to the low degree polynomials. So then you will compute this polynomial. How you can efficiently compute this polynomial? So entire those things, the computation is mainly is polynomial computation. Either you do evaluation on the given polynomial, or you give the vector or matrix, you compute the polynomials. Okay, then we will convert this polynomial to this circuit, R1CS circuit, to the polynomial, which is this. Then we will verify whether this is zero polynomial for all input in the affine space H. Okay. Then we'll have second convert to the polynomial satisfactions. So then because that the H, then we will put all zeros in this polynomial. Then you can compute this polynomial. So this equals 0, which means this polynomial divides this. So now, then we have this polynomial, then we will verify at a random point, which is the figure I just showed you before. However, this polynomial equal, but you only check at a random point, then this causes a soundness error. Okay, so that's how we bundle the soundness error. Okay, so now then the product check protocol also. This is many notations, so I will just go through fast. But this is the most important things, how you compute this polynomial. We employed something I called the sparse encoding. So in this ways, we can have very fast computation. Then once you get this 3 polynomial, A bar, B bar, C bar, then you can do the product of this 2 polynomial. So currently we haven't solved this problem, how we efficient to compute. So this is at least n times log n. Okay, then you do the division, get this G polynomial, then you will commit this G using any polynomial commitment. So this is also general framework. Then we can use any specific polynomial commitment. So now your random pickup point Rx, then you evaluation this 4 polynomials. Okay, so this is this 4 point plus your commitment, polynomial commitment. So that's a 5 element. So then verifier can compute this polynomial because this is just log n computation. Okay, so now he verified whether this is true. If this is true, he continue the univariate polynomial sum check. Okay, for the univariate sum check protocol, then basically is to check the validity of the VA, VB, VC. This is we do not check before, we just directly use. So how we check this? Basically, you random pick up the 3 elements, you form this equality. However, this equality basically is a univariate sum check. So you check this whether equal to C. Then this polynomial QX basically is the polynomial we encountered before. However, then we do not directly doing this one, QXY instead. We were using Lagrange interpretation to decrease the degree of the QX. Okay, so now then we get this PX. This is where we're using the low degree test to test the degree of this PX. Okay. Then after we have that low degree test polynomial, then we will commit 2 vectors. One is from the weightless, another is from that low degree polynomial testing. Then we will run the GKR protocol and to compute the values of this polynomial at the 4 point. Okay, so usually in the Aurora or others, because in order to, for the verifier to compute this, basically they need to access this polynomial. So that's the n complexity. Okay. So after using the GKR can reduce to the log n. Okay, so that's what we used. Then you compute this, then you can finish the final check. So final check is that low degree polynomial computed at this 4 point. Okay, so that's a very rough introduction to the Polaris. But the major part of computation is the polynomial computation. Okay, so this is our implementation. So we also using their package to get their performance, but we did not implement their schemes. We just run their code and get their performance. So currently we are trying to implement all different schemes. Then I believe that comparison will be more fair because it's the same platform. So currently they're using, we run their experiment, but it's their platform. So, but anyway, even this Polaris also shows good properties. For example, this is poor words time, which is compatible with the Aurora. And the Ligero has good, and the Spartan also good. The reason is the Spartan is a multivariate polynomial representation, and Aurora, the time is square root of n in this case, so he gets better performance for the poor word time. And for the proof size, then proof size and Ligero is the square root of the n. So you see, the other all other scheme is the log n. So the Spartan is this smallness. Okay, so that's the proof size. And for the verifier computation, the verifier original Aurora, you see, because the verifier needed to read that polynomial ax, bx, and cx. So that's why it's this. But for us, we use the GKR protocol, so that becomes a log n. So that's the Polaris. And this one is Spartan for the verifier's time. Okay. We did not put the worker here because the worker using the multiplicative group. So they're using Merson prime 2 to 61 minus 1. So they only can get less than 80-bit security because here our comparison always 128-bit security. Okay, so that's why we did not put a worker here. Okay, I guess then this is the example of their Zcash. So basically, this is UTXO. So basically, they created this thing is the pool. For the pool, then they will add the Gorse 16 proof here, and any miner will verify this Gorse 16 proof. But you can tell any zkSNARK can do the same job here as the Zcash did here. So that's I won't do the detail. So now I will wrap up. So for the blockchain privacy, basically the practical system in the real world is the work published in 2013. Because they have constant proof size and the verifier complexity. The only problem is they need the large CRS. We do not know whether this is good or bad. Depends, you trust them or you do not trust. However, one thing is clear, because they involve the very heavy crypto computation, and in the 2019, people found the vulnerability for their implementation in the Zcash. And the Zcash immediately make an announcement that they should not using that implementation. Instead, they implemented the Gorse 16. However, I think they only did in 2021 instead of 2019. And for the other schemes, like the Ligero or Aurora Fractal, those schemes, they do not need trusted setup. they do not need to perform heavy pairing crypto operations. And possibly they also has plausible post-quantum security because it do not rely on any hard computational problems. So possibly those approaches could eliminate those vulnerabilities in the implementations. Okay, and Polaris basically we improve the verifiers performance compared with Ligero and Aurora for R1CS circuit. And we only rely on the symmetric cryptography, either is collision resistant hash function or random number generator. Okay. And for the SHA-256 circuit, and if we're using the Polaris to verify this preimage, so that's I mentioned about the 23 AND gates with 128-bit security, and the proof size is less than 150 kilobytes, and the verification time less than 11 milliseconds. And those performance basically is compatible with those existing schemes. However, we have concrete verifier complexity. We are not bounded by that big O. We bounded by the constant which we can determine. Okay. Also, you can see entire computation is doing the polynomial evaluations or running the Lagrange interpolation to get polynomials. But these two operations, one is Lagrange interpolation corresponding to the inverse fast Fourier transform, and the polynomial evaluation corresponding to the fast Fourier transform. So in the coding theory, usually we implement those by linear feedback shift register. Okay, so this is the way we look at how we further reduce those computational complexity. So another way is currently those proof size only determined by number of multiplication gates. So one of the research direction people is doing is they look at the new hash functions, which has a small number of the multiplication gates. However, some industry people told me, they said, Guang, is that too heavy your tool? Then they think the zkSNARK for blockchain privacy is an overkill tool. But I do not know, at least in practice, that's only maybe possibly could other tools, but this is people think it is more practical compared with other crypto tools. And also they initialized some standardization activities and to standardize the zero knowledge protocols. So this is since 2018, then they have those activities. Of course, it's not initialized by list. Okay, so then for the Polaris, the content I took it from our new work, which just published in this year's the PAT. Okay, I guess that's all. Yeah, thanks.